Now we're going to take a look at the last part, which is hypotenuse-leg and some other theorems. Now, first of all, before we start, let's see if we can make a unique triangle from side-side angle. So side-side angle, you have your non-included angle, which is angle A. Now, I'm going to move this point to make a triangle. Well, when I move that point there, you can see that I actually did make a triangle. See, there's the angle, there's my side. There's my angle there, my two given angles and my non-included side. So the dimensions of that triangle are AC is 15, angle B is 75, and angle C is 64. Well, I'm going to go ahead and move it again and see if I can make a triangle again. And you can see that right here, it still stays on the same angle, and it has the side, it's the angle side, but it's different dimensions. It's a different triangle. So yes, you can make a second different triangle, and you can see it because this is kind of like a compass. This leg intersects at that angle 2 different times. Okay, so side-side angle is not a valid theorem. You cannot guarantee that 2 triangles be congruent. And how do you keep it straight? Honestly, a lot of geometry teachers will say, it's a naughty word backwards. So don't use the one that is a naughty word backwards. So how about hypotenuse-leg? Isn't that kind of like side-side angle? Because I'm going to have a right angle here at this point A. Well, let's go ahead and try that. Well, as you can see, I can make a triangle here. And so that's one of my triangles, right? And even if I intersect down here, is that a same or different triangle? I know it's hard to see this. There you go. It's the same triangle. So if I know the hypotenuse and the leg, there's only one way to make the triangle, which leads us to the hypotenuse-leg theorem. 2 different people using a set of congruent hypotenuses, or hypoteni, and one set of congruent legs are always going to make congruent right triangles. And so it looks like this, side, side. In fact, it looks like you only know 2 things. Why is that? Why does it work? Well, let's say I gave you a hypotenuse of 13 and a leg of 5. Could you find the other leg? Sure. Go ahead and use Pythagorean theorem, and it'll be 12, or you might even remember it's 12 because it's a triple. Well, since you can always find the missing leg when you know the hypotenuse and the other leg, you actually, when you know a hypotenuse and a leg, you know all 3 sides. So the hypotenuse-leg theorem is really a lot more like side, side, side. Now there's also a leg-leg theorem. Does this one work? If I just know it's a right triangle and I know one leg and the other leg, could I actually say, yeah, that's good enough? Well, yes, because see this angle here and this angle there, they're both right angles, so they're congruent. So this looks a lot like side, angle, side. Now in this example, you have 2 right triangles that are overlapping, EBC and ADB. And I tell you that EB is congruent to BD and AD is congruent to CE. And I'm trying to figure out how to do the congruence statement and justify it. Well, when you're dealing with overlapping triangles, the best thing to do is to draw them separately. So you can see ECB matches. ADB here matches. So now I'm going to use these 2 statements to fill in my marks. EB is congruent to BD. See, I have my 2 matching sides. AD is congruent to CE. Now, you might be tempted to say the 2 triangles are congruent by side-side angle, but that's not a valid theorem. But because these are right triangles, we can say that they're congruent by the hypotenuse-leg theorem. And so start, if it's ADB, see how I cross through the 2 hash marks, then through the 1 to the right angle, so cross through the 2. See, I don't want to start down here. I want to start up here because I have to go through 2 marks, 1 mark, then right angle. 2 marks, 1 mark, then right angle. If I had started here, I would have done 2 marks, no marks to right angle, and then 1 mark. So that's not how I do that congruence statement. You should be going through the marks in the same order. So now finally, is angle, angle, angle good enough to prove that two triangles are congruent? We had side, 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 angle, angle, side, angle, 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 side, not side, side, angle, and hypotenuse leg. Are three angles enough to prove they're congruent? Well, I told you, draw a counterexample, so you can guess now. I'm going to start with the ultimate counterexample, the equilateral triangle. So these two triangles are congruent. Well, and definitely all the angles match. But if I take this point here and make it bigger, you can see that my equilateral triangle here still has matching angles, but the sides don't match anymore. I could have done a scaling triangle as long as I kept the angles the same, but I think it's really obvious for equilateral triangles. Not all equilateral triangles are congruent, even though all of their angles match. So for further reflection, why doesn't the side-side angle work to prove triangles are congruent? Why does hypotenuse leg work even though it kind of looks like side-side angle? Why does leg-leg theorem work? And when working on overlapping triangles, what should you do? What strategy should you use? And then what other theorems and postulates are helpful in showing angles and side congruences? Remember, reflexive property is big. Vertical angle theorem is big. Maybe definition of an isosceles triangle, so you know two base angles are congruent or two legs are congruent. And finally, why doesn't angle, angle, angle work to prove triangles are congruent?